the most tedious part comes. Interplay between SPM and the GVD. Okay. So how about the motivation? Why should we consider this complicated case? So let's review the SPM formula. The phase modulation is equal to this one, but be careful. This formula is valid only when your intensity profile does not change with propagation. And this is no longer true in the presence of GVD. If you consider SPM only, assuming no GVD, then your pulse intensity profile does not change, right? It only changes the phase. It does not change the intensity in the time domain. Then this formula applies. The problem is in practice, both GVD and SPM coexist, right? Then this assumption is no longer true. Your intensity profile actually changes with propagation. Then this formula can no longer apply. Do you know, can you justify why, when I of t changes with time, this formula is no longer true? I can think about maybe two reasons. If you have an intensity profile like the red one, you will see a temporal phase like the blue dashed curve, right? But what happens if the red intensity profile changes with time? Can you still obtain the phase modulation like the blue curve? No, because, for example, your pulse shape changes gradually from a narrow Gaussian to a broader Gaussian because of GVD. Then, how could you maintain the shape of your SPM phase modulation, right? 你在传递的过程，你这个脉冲的形状一直变。那假设最简单，它变胖好了，它变胖，那我对应的 phase curve 也要跟着变胖才对啊。That's the nature of SPM. Then you have many different intensity shapes, so you can never have a unique phase profile, right? So the simple formula will not work. That's one reason. The other, what is the other reason? Okay, for example,
It no longer triplets.
No longer triplets. If you have SPM, it must be chirped. OK， 所以本来就是 chirp pulse。即使你打进去是没有 chirp， 有了 SPM 它也一定会变 chirp， 所以本来就无法排除 chirp 的可能。The second reason is actually quite intuitive. Imagine if you have an input pulse like this. So your phase curve should be defined within this range only. For the region outside, there is no power, there is no phase, right? But during the propagation, if there is GVD, your pulse will be broader and broader. So the time window will be increased. So you will face the trouble. 你在一些原本没有 power 的地方，现在要出现 power， 它就有 phase。可是你原来这个 curve 是没有 definition over those time window, right? So this curve should not apply if your pulse shape change with propagation. So there is a necessity. We have to include both mechanisms instead of one at a time. Sorry. The other case is similar when we mention that the contribution of GVD is a phase modulation in the frequency domain minus beta of omega times L, it's assumed that your power spectrum does not change and your index does not change as well. Okay? For example, if your index changes, then beta of omega is not unique. Beta of omega equals index times wave number in vacuum, right? If your index changes with propagation, there is no unique beta. Then this formula does not apply. 你找不到一个唯一的 beta 嘛，对不对？每一个 frequency 要找一个 beta， 这个公式才能算啊。可你现在的折射率可以因为 cell phase modulation 而改变 ，right? Your index changes with propagation, then there is no unique beta. And besides, your power spectrum will change with SPM. So you will see something as I just introduced. If you have SPM, your bandwidth is broadened. So you will generate new frequency components. And in those frequency ranges, there is no definition about phase in the beginning. Okay, so there is a conflict. So how do we overcome, or how do we analyze the case? You have to solve the nonlinear Schrödinger equation, NLSE. I have shown the equation here. Beta 2 describes the contribution of GVD. Gamma is related to Kerr coefficient N2, so it describes the contribution from SPM. You have to solve this equation, okay? And it will take both mechanisms into account, both GVD and SPM, okay? And by solving that, you can figure out the evolution of the pulse envelope, small a as a function of position z and time t. So your shape, at the beginning z equals 0, you have some shape. At the output z equals L, you will have a different shape. And in between, step by step, you have to solve a of zt by solving the NLSE, nonlinear Schrödinger equation. So let me show you 3 different examples. The first example is we have SPM and we have anomalous GVD. And you will see the phenomenon referring to solitone. Okay? The idea is quite easy. Cell phase modulation must give you upchirp. Your local frequency will increase with time. And the anomalous GVD will give you downchirp. Your local frequency will decrease with time. So they are in conflict with each other. So imagine if the 2 forces happen to be balanced, everything will be fixed, maintained, right? That's the idea of solitone. Here we define several parameters. LD is the dispersion length defined here, pulse width square over GVD parameter beta 2. LNL means nonlinear length. It's inverse of gamma times peak power. Gamma is the SPM parameter defined in the previous page. Okay? But what are the meanings? LD means the distance over which GVD is important. LNL means the distance over which SPM is important. OK? 好，所以这2个数字是在描述说，到底作用距离有多长啊？有 LD 这么长，色散就重要了；比它短，色散就还不重要啊。那 LNL 是在讲距离超过了它。SPM 就很重要，比它短就不重要。Okay? So the shorter the LD, the more important the dispersion, right? 如果这个距离越短，就是很容易超过 LD， 那这个色散就很严重。So you can see when beta 2 is bigger or TP is smaller, you will have a shorter LD. Larger beta 2 is the material is more dispersive. Shorter pulse width means the bandwidth is broader. So both will incur stronger dispersion impact, right? And for the same thing, if you have larger peak power or larger SPM coefficient, you will have a shorter nonlinear length or a stronger SPM effect. Okay. And another parameter is called solitone order, big N, which is square root of LD over L and L. So basically, it describes the relative strength of SPM over GVD. If this is smaller, you will have a bigger N, right? 所以意思是越小的 nonlinear length 代表越强的 SPM。所以这边在这个 big N 描述的就是 SPM 相对于 GVD 有多强。The bigger the big N, the stronger the SPM, basically. Okay. So as I mentioned, if the power of SPM happens to balance the power of GVD, quantitatively it means big N equals 1, happens to be equal 1. They are balanced. Then there is a unique second hyperbolic pulse characterized by this formula. Okay? Some peak electric field times second hyperbolic function of T over Tp. Okay, so you have certain peak power, certain pulse duration, and this second hyperbolic pulse can propagate without distortion over a very long distance, just like this figure. Okay, this is the time axis, so this means the input pulse, and during the propagation, the pulse maintains its shape, maintains its amplitude, maintains its pulse width without distortion, because the force of SPM happens to balance with the force of GVD. 所以本来这两个力量都在哦，只是它刚好平衡，所以所有的事都卡在那里，它就变成所谓的光孤子或光固子，optical solitone。这就是薛定谔 equation 的 solution。你把它带进去，它会符合。但是 be careful, you have to maintain certain peak power, certain pulse duration. OK， 所以这个条件很严格。OK。Second example, you have cell phase modulation. But this time you have normal GVD, then you will incur so-called wave breaking. Okay. So what is that? Assuming we have an input pulse, which is chirpless Gaussian. In the time domain, you have a Gaussian pulse. In the frequency domain, you have a Gaussian spectrum. And the middle one means the instantaneous frequency shift. And it comes from the time derivative of your temporal phase. But we have already assumed input pulse is chirpless, so there is no frequency shift. 就是你的 local frequency basically 是常数，不会随时间改变，没有 chirp. This is the input pulse. If there is cell phase modulation, what happens? We have known you will incur instantaneous frequency function like this curve, right? 如果你有 SPM， 你有一个高斯的 intensity， 你就有一个反高斯的 phase， 再微分就得到它嘛。我们已经做过这件事 ，right? And you can observe at 3 occasions, the pulse lead, the pulse center, and the pulse tail. You will see the carrier frequency, or green color. there is no frequency change. And this is red, right? And this is blue. Okay? So with SPM only, you will see this case. But now, not only SPM, but also normal GVD, what happens? We know the meaning of normal GVD is red will travel faster than the blue, right? So where is red? Here. Traveling faster. It means the red component will move to the left earlier time, right? And for the same thing, same reason, blue will travel to the right to the later time. So that means the power at here will shift to the left edge. Power at here will shift to the right edge. So what would you have? Your power in the time domain will be redistributed with sharper edges, okay? Like this. Starting from a Gaussian pulse to a pulse with sharper edges because of this effect. And this is only true when you have normal GVD. Previously, we ignore GVD, so there is the pulse remains Gaussian, no change, right? And in the frequency domain, you will see something like this. Broader spectrum due to SPM, and the rippled spectrum, again, due to SPM. Okay. And if this feature continues, what would happen eventually? 这个红的会越跑越左，蓝的越跑越右，那最后会怎样 ？Okay. The edges of frequency shift function get increasingly sharper and sharper during propagation, right? So eventually, the red and the blue will overtake the leading and the trailing green like this. 红的已经追上了一开始的 post lead， 就是绿色的地方。Blue 呢也追上了一开始的 post tail， 也是绿色的地方。所以你就出现了这个奇怪的现象。At one moment, maybe you have multiple frequencies. Okay? And that is so-called wave breaking. You may have the experience about wave breaking. It's about surfing, 冲浪。那个海浪一开始是一个 function, right? 然后海浪的这个速度越跑越快，会追过去，最后会怎样？就变成不是 function 了。你一个轴切上去，你看到卷过来的，你看到好几个焦点，这就是 wave breaking. And this is exactly the same thing, but in the optics domain. Okay. So in the time domain, you will see a square pulse with very sharp edges. In the frequency domain, you will see something similar, still broadened but rippled spectrum. 所以 spectrum 比较看不出它的特质，那但是 time domain 可以看得很清楚，最后演变成几乎像一个 square pulse. That is wave breaking. Any question? So finally, how about the impacts of soliton and wave breaking? Okay. Soliton effect is important not only in the pulse propagation, because it will propagate without distortion over a long distance. For a period of time, it was very popular for telecommunications. Imagine you want to transmit your data over a long distance. If you want to save the cost of repeaters, this could be one of the choices. If your pulse can propagate without distortion, you do not need many repeaters in between. Repeater 就是走一段，你的脉冲变形了，你要把它救回来，对不对？救回来再继续走。If you propagate with soliton, you do not need repeater. Okay? But it's also useful in the pulse formation, in the absence of self-amplitude modulation. Actually, in the textbook, Chapter 7 is dedicated to solid-tone fiber lasers. 就是说有一类的脉冲 laser， 它产生的机制就是靠这个 solid-tone。It does not need a Mohr-Lacher saturable absorber. It does not need. Just a long piece of fiber with anomalous GVD. The solid-tone effect will automatically form the pulses from noise. OK， 所以这有一类的 laser 依赖这个机制来产生 short pulse. So not only propagation but also formation. How about wave breaking? It's detrimental, it's harmful because it will disturb Mohr locking. Okay? So if you design a laser, you will try to prevent wave breaking from happening. What happens if wave breaking occurs? You will get trouble because the signatures of wave breaking is 1, you will have square pulse in the time domain, very sharp edges, right? 2, you will have rippled spectrum in the frequency domain. And inside the cavity, you have to satisfy the self-consistent condition. Pulse has to repeat itself every round trip, right? If you have wave breaking, you can imagine it's very difficult to satisfy self-consistent condition. 这么烂的 shape 要怎么让它每走一个 round trip 都回到自己，非常困难。所以它会严重干扰你的这个 Mohr locking. Okay, so one of my research interests over the past years is how do we increase the intracavity pulse energy without incurring wave breaking? Once that happens, the laser is destroyed. But when you try to increase your pulse energy, you will incur stronger and stronger SPM. And wave breaking is very easy to happen. So we have to combat with wave breaking.